Doctor. Very kind of that lady. Dr. Martin Weigt from University of Port Elizabeth. It is in South Africa. Am I right, Martin?
Yeah, Nelson Mandela University.
Which one?
Nelson Mandela.
Nelson Mandela. Yes. And by the way, stupid question. Shaka Zulu, when he was a king, he held. Did he hold this area where now is your university?
That's actually further north in another province, which is the same. That's KwaZulu-Natal, where the same province in which Durban is.
Yes. I understand. So yes, Dr. Martin will has his lecture. He will remind us the title, and he will begin, as we hope. So please.
Okay.
Yes, we are.
All right. Then I just need to share my screen.
Yes.
Okay.
Yes, please.
Just need to see your share screen. Okay, yeah, I'll do that quickly now.
Yeah.
Everything here. Okay, share.
Zoom, it is written. Yes.
Can everybody see the screen?
Yeah. Yes, I see at least. Yes.
Okay. Okay.
Okay, please.
Right.
Good.
Okay. Excuse me. Yeah, my audio is on. All right.
Yes.
I would first like to thank the organizers, that's Professor Hilemski and Professor Perkowski, for allowing me to give this presentation tonight. And also
invite. We're very pleased that you consented to us.
And thank you also for your encouragement to participate in the seminar. So I also hope to listen to future presentations which will take place as part of the seminar. But thank you again very, very much for inviting me as a speaker and for allowing me to give this presentation.
Yeah.
No, thank you for accepting our invitation.
Thank you. My pleasure. What I'm going to talk about today has more to do with unbounded operator algebras in the abstract sense. What we are mostly all familiar with C-star algebras like von Neumann algebras and von Neumann algebras, but when we go to unbounded operators, unbounded operator algebras, that is now where things become a little bit more hazy, if I can say. The concepts become less clear-cut, and also the arguments become more challenging and involved. And also working with unbounded operators is what is important for mathematical physics, quantum mechanics, quantum field theory included, of which I will say a little bit more toward the end of this talk. So what we will talk mainly about are the generalized B-star algebras, which are actually generalizations of C-star algebras. Okay, hence B-star in the abstract sense. So before I continue, a lot of what I mentioned in this talk was first initiated by Graham Allan in about the late 60s, 1967, round about there, and then it was reinvigorated a few years later in the early 1970s by the late Professor Peter Dixon. Okay. So, and also recently, Maria Fragolopoulou at Sushi in Norway and Ioannis Zarakas, we published a monograph together, a joint monograph on this topic, as previously all the literature on this topic on generalized B-star algebras which exists, it exists in the form of various journal articles which are scattered across various journals. So what we then did was we actually took all those articles, we put them all together to put them coherently together, and also to include some of the latest work which we've been doing. So this book has been published last year in the lecture notes in mathematics series in Springer. So if you would like me to send you the flyer after the talk, then you can just drop me an email and I can do that. Okay. All right. So first of all, I'd like to just start with setting the scene with the basic concepts. So by a topological algebra, we mean an algebra which is a Hausdorff topological vector space. So there's a topology on it, making the addition and scalar multiplication continuous, and the topology Hausdorff, but in such a way that the multiplication is separately continuous. Not necessarily jointly continuous like we have for addition, but only continuous when one variable is kept fixed at a time. And then a locally convex star algebra will be a topological algebra having a continuous involution in such a way also that the underlying topology gives us a locally convex space. So a Banach star algebra would be a typical example of a locally convex star algebra, but now, of course, we are going into the non-normed scenario. Okay, so we start with how GB star algebras have first begun by Graham Allan, 1967. Okay, so I'm going to use the term GB star algebras as a short form for generalized B star algebra. So what you do is you start here with a locally convex star algebra A tau. So tau is the topology on A, making it a locally convex star algebra. And then what we do is we let this color graphic B star here denote the family of all subsets B of A, such that B will be first absolutely convex, and the square of B is contained in B. So in other words, it's idempotent. It's closed under multiplication, and also it's B star equal to B closed under involution and contains the identity element. So unless otherwise stated, all our algebras will be assumed to have an identity element. And secondly, B is also closed and bounded. So this color graphic B star are all those sets which are absolutely convex, bounded, closed, and which are idempotent, closed under involution, and has the identity element. Now I want to introduce a form of completeness, which is not quite the usual form of completeness, but you can say it's like a half form of completeness, if I can say. We'll say it's pseudo A tau is pseudo completeness if, first of all, this set over here is a Banach star algebra when we consider the Minkowski functional norm B on B for every B and B star. So you give me any B in B star, and if norm B over here, the Minkowski functional, is always complete on that set, then, in other words, a Banach star algebra, it's pseudo-complete. I should mention here that this will actually always turn out to be an algebra because of the properties of B over here, being closed, bounded, absolutely convex, etc. It's a normed algebra always under the Minkowski functional, but the moment it's complete, in other words, a Banach star algebra, and this is true for every such B and B star, we call it pseudo-complete. Every locally convex star algebra which is sequentially complete can be shown to be pseudo-complete. So that's also why we say it's like a form of pseudo or half completeness, really. It's not quite complete, but we have it true for at least all sequentially complete spaces. Okay, now that I've set the scenery, I'm now going to continue with a locally convex star algebra, which is pseudo-complete. If you do flip through the book of Walbrook, Topological Vector Spaces and Algebras, then sometimes pseudo-complete will be referred to, this thing being Banach, the B will often be referred to as completant. Okay, so for those of you who are familiar with that reference. Okay, now we start with a unital pseudo-complete locally convex star algebra. We will call it a GB star algebra. If, first of all, you can find a C star algebra denoted as norm as A subscript B under some norm, C star norm, which is contained in A, in such a way that if you give me any element X in A, then 1 plus X star X is necessarily invertible in A. In other words, its inverse exists in A. But not only the inverse must exist in A, the inverse has to exist within that C star algebra. And this is true for every X in A. So if we remember a C star algebra, if you take X in A, B, then we know this. Then we know that this inverse of 1 plus X star X is in A, B. But we are not just saying it's true for the elements in the C star algebra A, B, but every element X in A. In the GB star algebra, what we call GB star. And then secondly, the unit ball of AB, that's the closed unit ball, is the greatest member of calligraphic B star with respect to set inclusion. So when going back to this class of sets which I had on B star, then the closed unit ball of this AB is the biggest element of that set when looking at set theoretic inclusion. In other words, what we see here is a GB star algebra is like you take a C star algebra, but now you are making it bigger by throwing in other elements. And those other elements I will explain a little later on are actually in disguise unbounded operators. It's actually coming down to a generalization of the non-commutative Galfand-Neumark theorem. So it's like you're chucking in unbounded elements, if I can say, making it bigger with that. It's worthwhile to mention here that if AB is a GB star algebra, then when I take this topology tau on the GB star algebra and I restrict it to AB, in other words, we look at, on AB, we look at the relative topology coming from tau, then it will necessarily be weaker than the norm topology on the C star algebra. Okay, one other thing I'd like to talk about is the idea of taking spectrum. When we work in a Banach algebra and we take the spectrum of an element, okay, we say lambda isn't the spectrum of X if X minus lambda 1 has its inverse in the Banach algebra. But when we go to the non-normed case, then one can work with that same type of spectrum, but we find that that spectrum is not so well behaved. It has certain shortcomings that certain things which make things work in a Banach algebra won't necessarily work in a locally convex algebra. So it falls short. It's sometimes the wrong spectrum to work with. And that's especially if you want to do spectral theory in locally convex algebras like you do in a Banach algebra. Then that ordinary spectrum, which we are so accustomed to in Banach algebras, is not quite the right one. So we have to work with another type of spectrum. And this is also, this idea is what Allan used also, but it goes back to Lucien Walbrook. So we start with a pseudo-complete locally convex algebra with identity. Now this symbol A0 will mean the set of all elements X inside this locally convex algebra, for which you can get a non-zero lambda, such that this set, which I've displayed here, is a bounded subset of A. So this set runs over all the natural numbers. What Allan realized he had to do was to find the right concept of bounded operator or bounded element, the right notion of spectrum in order to do some good spectral theory. And notice here we are looking at a general pseudo-complete locally convex algebra. The Allan spectrum, sigma AX, okay, so you can even call it the Walbrook spectrum. It will be the set of all, first of all, it's the union of two sets. It's all complex numbers lambda for which that inverse exists and belongs to A0. In other words, the inverse exists and is bounded. It's a bounded element in the above sense. And if X is not a bounded element, then infinity will be included in the spectrum, but only when X is not a bounded element. So now suddenly infinity starts making its appearance. And also this idea of a spectrum very closely parallels the spectrum of an unbounded operator on a Hilbert space or Banach space. It parallels that very closely, so that we actually are doing, we've got the right concept of spectrum to make things work in a locally convex algebra, especially in which to do complex analysis, in which to get a functional calculus and so on. That's something I will mention a little bit later in this talk. Again, this does show that going to the non-normed case, then what we are so familiar with and so accustomed to with Banach algebras, there can be more than one possible generalization, and which one do you take? Okay, some examples of GB star algebras. Now we come back to that. First, there are what we call the pro-C star algebras, which are complete locally convex star algebras, for which tau is defined by a family of C star seminorms. Very often we take it to be a directed family because then such an algebra can be expressed up to topological star isomorphism as an inverse limit of C star algebras. So this goes back to Inoue and Schmutgen in the early 1970s. I think probably even Ahrens. C of X with a topology weaker than the compact open topology, where X is a completely regular Hausdorff space. This, in fact, turns out to be a pro-C star algebra, commutative, but it's actually, you could say, a prototype of the commutative pro-C star algebras. Let's have a look at GB star algebras which are not pro-C star. That would be the intersection of all LP spaces. So that would be where the topology on L omega is defined by the family of LP norms. And the underlying C star algebra in this third example would actually just be the L infinity space of 0, 1, which is also a W star algebra or abstract von Neumann algebra. So that would be the underlying C star algebra of that. And the closed unit ball of that space, L omega, is then the essential supremum of those measurable functions bounded less than or equal to 1. But it's not a pro-C star algebra because this algebra does not have continuity of inversion. It does not even have characters. And in the commutative case, a pro-C star algebra has continuous inversion, has characters. And then you can construct many more examples by just taking any unital closed star subalgebra of a GB star algebra. It's again GB star. Like any closed C star any closed star subalgebra of a C star algebra is C star. And now there are more examples which I'm going to discuss.
Mm-hmm. Oh. Mm-hmm.
Okay, one more which I want to introduce before I come to the more non-commutative integration theory part is it can sometimes be very difficult to look at the structure of a GB star algebras where there are no C star seminorms because they are so well behaved and so easy to work with. So we start looking at the next best thing. you look at a directed family of seminorms having the property that for each lambda, there is a lambda prime in lambda, such that for all xy in A, p lambda of xy is less than equal to p lambda prime x, p lambda prime y. So in other words, you give me any seminorm p lambda, then you can necessarily find another seminorm p lambda prime, which adheres to this inequality for every x and y. So the moment I change the seminorm p lambda, in other words, I change the lambda, then I could end up with a different subscript or a different seminorm p lambda prime. And of course, the same p lambda prime satisfies the second and the third condition. And then what we do is we call A tau a C star-like locally convex star algebra if it is complete. And if you look at the following set over here, the set of all x for which the supremum of p lambda x is finite, that this be dense inside the locally convex star algebra. So this family is not quite, they're not quite submultiplicative, but they are like kind of submultiplicative. Furthermore, this AB can be shown to be a C star algebra, so to be norm complete, in other words. In the norm which is then defined by the supremum p lambda x. As one example of a C star-like locally convex star algebra, that would be the L omega space on the previous slide, that Aaron's algebra. That's one example of such an of a locally convex star algebra. So these were investigated in about 20 years ago for the first time, and some representation theorems were given. Okay, now let's get down to some more non-commutative measure theory. Let us now start with a von Neumann algebra, which has a faithful semi-finite normal trace.
Mhm.
And you can think of it as a non-commutative integral on an L infinity space. And now what we do is we consider M tilde here to be the set of all closed, densely defined linear operators affiliated with M, so that for any delta larger than 0, you can necessarily find a projection P in the von Neumann algebra, such that the range of P is contained in the domain of X. So X would be, X is now it's a set of all operators of X affiliated with M, and such that the trace phi of 1 minus that P is less than or equal to delta. So in other words, that projection P that you get here, which is in the von Neumann algebra, in the domain of X in M tilde, that depends on the delta that you start with. And phi is, again, the faithful semi-finite trace. And then we call M tilde the set of all phi measurable operators affiliated with M. This has also been a widely this has been widely studied, this class of topological algebras, also from the non-commutative Banach function space point of view. I want to say a little bit more about this. These phi measurable operators, they actually can be equipped with a topology of convergence in measure, which again generalizes topology of convergence in measure on the equivalence classes of measurable functions on a finite measure space, at least that. So in other words, this topology has as a basic neighborhoods of 0 the sets M tilde epsilon delta, and we define the M epsilon m tilde epsilon delta to be the set of all x and m tilde, all phi measurable operators of x, for which you can get a projection P whose range is contained in the domain of x, and such that the norm of xp is less than equal to that first epsilon you set there, the first argument, and so that the phi of 1 minus p is less than or equal to the delta being the second entry in this m tilde epsilon delta. In other words, the p is what you get according to the choice of the epsilon delta that you've got here. So in other words, these must be the basic neighborhoods of zero. We call it the topology of convergence in measure on m tilde. And it's actually the non-commutative version thereof from the measure theoretic setup. Okay, now, if you take such a von Neumann algebra on a Hilbert space having a faithful semi-finite normal trace, then one can show that this m tilde is a Frechet GB star algebra in the topology of convergence in measure, I'll call it TCM, over the closed unit ball of M. But one must be cautious here, and now I'd like to mention, for us a GB star algebra is a locally convex algebra. That's how we started off with in the first place, Allan's definition. But in the early 70s, Dixon actually generalized the notion of GB star algebra to also include the non-locally convex algebras. So the moment if you look at Dixon's generalized definition to include the non-locally convex algebras, then this m tilde, the phi measurable operators affiliated with M, will in fact be a Frechet GB star algebra in the sense of Dixon, because this algebra here, m tilde in the topology of convergence in measure, is not necessarily locally convex. But in the event that this is locally convex, then it will be a GB star algebra in Allan's sense, our definition. Again, if you look at M to be the L infinity space 0, 1, then m tilde can be taken to be the equivalence classes of measurable functions on 0, 1. And then the trace will just be the integral on that space L0. So this is actually how non-commutative measure theory can fit into the framework of these generalized B star algebras. Okay, if we stay with a von Neumann algebra, but now with a faithful but finite normal trace. And again, you can look at the m tilde, the star algebra of phi measurable operators affiliated with M. Then one can actually come up with a non-commutative Arens algebra, which is this LP M of phi, all x in m tilde, so that if I look at the trace of mod xp raised to the 1 over p, then this is finite. So this also places a restriction that the operator must be bounded. This actually then is a direct copy over of, this is like the non-commutative, the commutative LP norms, and then we look at the corresponding LP spaces for all P. That's now for 1P. Now you can take the intersection of all these LP spaces, call it L omega, and this turns out again to be C star-like locally convex star with respect to this family of C star-like seminorms. Again, just a direct carryover or generalization from the Arens commutative algebra. And this is also C star-like. So the seminorms are not quite submultiplicative, but in a sense submultiplicative. All right, so, okay. So that means actually for those of us who work also in non-commutative measure theory, then one can actually, if you view those things as a GB star algebra such as that, then you can apply general results about GB star algebras to this algebra to solve problems, in the same way that we apply general results about C star algebras to solve certain problems. Okay, now I'd like to start looking at representation theorems for GB star algebras, which are generalizations of the Gelfand-Neumark theorems. The first one by the late Graham Allan, 1967. If you start off with a commutative GB star algebra, then this Gelfand map, the well-known Gelfand map of the underlying C star algebra AB, extends to an algebra star isomorphism of A onto a star algebra of functions on the maximal ideal space of AB. This Gelfand map over here, actually, this extension, or I should rather say the extension here, is actually just an extension, therefore, of the Gelfand map, but now with the difference that on A, the characters need not be finite valued, but they can take on the value infinity on a set which is nowhere dense. Okay, so in other words, we will still use the same symbol x hat, but now it's defined on a character of A which can take on the value infinity. Okay, so now this then is how one can then extend, one can then have a commutative representation theorem for such algebras. So it could be that the algebra in question, such as L omega, it has no characters in the sense that there could be no character which is finite valued, but you will certainly find characters which take on the value infinity. Except when you work with this type of representation theorem, things become more challenging because of the infinity that keeps cropping up. As for the non-commutative GB star algebras, I would like to show you two versions of the representation theorem to the non-commutative case. But in the C star algebra case, they both turn out to be the same thing. But when going to the unbounded case, one actually should make a distinction between the two. There are two different versions floating around, which are the same in the C star case. So let's start with the GB star algebra. And for us now, GB star algebra will mean in the sense of Allan, and therefore locally convex, pseudo-complete. But it also holds true in the more general GB star algebra definition of Dixon. You can find, which is locally convex, you can find a faithful star representation, call it pi of A, onto some unital star algebra B of closable linear operators, which map some inner product space D to itself, and such that the adjoint operator X also maps D to itself, no matter what X and V you take. And then the involution on B, which makes this a star algebra, will just be the ordinary adjoint operator of X as an unbounded operator restricted to D. And we can see this makes sense because X star maps D to D. And we want all operators to map D to D. That's the one representation theorem which Dixon gave. The second one which he gave builds directly on this theorem which you see on the screen. Using this, he then managed to obtain a second representation theorem of a GB star algebra. There's a faithful star representation of A onto a star algebra of closed linear operators on a Hilbert space, but now with a common domain. In other words, now all those operators can have different domains, but one can take the intersection of all those domains, and then there's a common domain which is dense in the Hilbert space. And then the elements of B0 will correspond to the closed unit ball of the image of A under pi. Both of these theorems coincide in the C star case, but now again, going to the non-normed or to the world of unbounded operators, there can be more than one generalization. And one generalization can be fit for purpose for one application, but not for another. And now things become trickier when having to work with unbounded operators, especially because now the domains can be different. Okay, so then these are the generalizations of the non-commutative Gelfand-Neumark theorems. So these things are starting to look much more like C-star algebras. Also, many other results that we have for C-star algebras do carry over to GB-star algebras, but not necessarily all of them. Okay, and I will now mention a couple of results, which is also work which I carried out with one of my colleagues, that's Ioannis Zarakas, who also is a former doctoral student of Maria Fragolopoulou. Okay, first, I'd like to just to give a summary here of what do we know about derivations. These things are important for mathematical physics as they are generators of star automorphism groups, which of course are coming from Schrödinger's theory of quantum mechanics. A derivation will be any linear map going from A to A, which satisfies this generalized product rule from calculus. And then all derivations of a pro-C-star algebra can be shown to be continuous. I can remind you here that on a C-star algebra, we know that they're all continuous, and then Becker managed to show this for all pro-C-star algebras. And then the zero derivation is the only derivation of a commutative pro-C-star algebra. Much like when you take a commutative C-star algebra, then again, the zero derivation can be the only derivation there. No non-zero derivation. And then a star derivation of a pro-C-star algebra is the generator of a one-parameter group of star automorphisms of A. Okay, then about 10 years ago, then my colleague and Ioannis Zarakas, myself, we managed to extend the previous results by showing that the zero derivation will be the only derivation of a complete commutative GB star algebra, but now where the multiplication is jointly continuous, not only separately continuous. Okay, this extends the previous result of Becker because in a pro-C star algebra, we have complete, and there we have jointly continuous multiplication. As a corollary to this, if you take any commutative Frechet GB star algebra, then the zero derivation is the only derivation of A. Here, Frechet means complete and metrizable. In some other references, it could mean complete metrizable and locally M-convex. But for us, it's only complete metrizable. And in a complete metrizable algebra, one necessarily has that the multiplication is jointly continuous. So this is why this theorem follows directly from, the corollary follows directly from the theorem. Again, it generalizes what we know in the C star case. Every derivation of a C star algebra in the commutative C star algebra setting can only be the zero one. Okay, but now what about the non-commutative case? This actually turns out to not be so clear-cut yet. And that's where there is an open question. So is every derivation of a GB star algebra continuous? Okay, so for that, we'll give a special case. We will call a GB star algebra A nuclear if the underlying C star algebra of A is a nuclear C star algebra. Then in this case, we have managed to see that every derivation of a smooth, take note of the word smooth, Frechet nuclear GB star algebra is continuous. Okay, so by smooth, we mean actually that if we any defining family of seminorms gamma, if you give me a defining family of seminorms gamma, there is a defining family of seminorms gamma such that for every seminorm P in this family, you can necessarily find a seminorm Q in the same family so that you have this inequality here, P of xy less than equal to QXPY for every x and y in A. So here especially we have jointly continuous multiplication. We were actually drawn to considering this form of joint continuity of multiplication from one of the papers of Christina Podara, who's also one of Maria Fragolopoulos' former doctoral students. And she carried out an extensive study of looking at bimodules and algebras which have a family of smooth seminorms. So all what we want is we just want to know that there's at least one defining family of seminorms having this property here, then we call it smooth. In this proof here, we've had to consider A as a locally convex bimodule over AB to make things work. And then also later we showed in the same year, we saw every derivation of a Frechet GB star algebra where the underlying AB is a W star algebra is inner. Inner means that there is an element A within A so that delta, the derivation delta is the form of a commutator for all x in A. These are actually the simplest types of derivations around, especially in the non-commutative case. So if we know that every derivation is inner, then we know that all derivations are, the structure therefore is very simple. There are those commutators. It makes it easier then to work with. In a von Neumann algebra or W star algebra, we know that all of these algebras are inner. And to prove the result here, we've had to again make use of non-commutative measure theory, and in thinking of A actually as a star subalgebra of locally measurable operators which are affiliated with some underlying von Neumann algebra. Okay, now I will just make a brief mention about something on unbounded derivations of GB star algebra. This again goes back to my colleague, Ioannis Zarakas. And this was a paper that we published in the Barnach Journal of Mathematical Analysis. Now we are coming back to the notion of spectrum, the Allan spectrum, which I had mentioned earlier on in this talk. So one starts here with the GB star algebra. So let's say, and it's complete. And it has jointly continuous multiplication. And now what we do is we don't consider a derivation to be defined on the whole algebra A, but only on a part of the algebra, which I indicate by d delta. And this is actually dense. It's a dense star. This d delta is a dense star subalgebra of A. And this is now taken to be a closed star derivation where 1 is also in d delta. So 1 is in d delta. D delta is a dense star subalgebra of A, and then this derivation must be closed, a closed star derivation. Then if we now take f to be, if we now take a normal element x, and we take any function f which is analytic on a neighborhood of the Allan spectrum of x. So this fx here means the set of all functions analytic on a neighborhood of the Allan spectrum of x. So you take any such f and x is normal, then one can show that f of x is in the domain of d delta. This is one of the results that we proved in our paper. There was also another result that we have shown where instead of working with the Allan spectrum, you work with the usual algebraic spectrum, but then you have to assume continuity of inversion. And then we also had to, then we also proved some other results regarding pro-C-star algebras. But this is certainly what the result you see on the slide here is certainly one of the most important results in our paper. Okay, right. So I will now mention something about tensor products of GB star algebras. This is actually work that was started by Maria Fragolopoulou and Atsushi in Norway back in about 2009. Okay, so, and you can also find what I'm mentioning here, you can also find in our book. So that's also to be found in our book, which was recently published. Okay, and also I will mention the significance of on tensor products just very shortly when discussing some of the mathematical physics applications. Okay, now it's important that from here on, unless I say otherwise, every locally convex star algebra will be assumed to have multiplication which is jointly continuous, not only separately. That becomes useful because we want to, at some stage, take the completion of an algebra, and that completion will not necessarily be an algebra if the original topology on A is only separately continuous, especially below. So if you take A1 and A2 to be locally convex star algebras, then this over here, if I now look at A1 tensor A2 under tau, and the hat over here means the completion thereof of the algebraic tensor product under tau, this will be locally convex star algebra with respect to some star admissible topology tau on the algebraic tensor product. Okay, I will now show you on the next slide what I mean by a star admissible topology. And it actually comes from the theory of tensor products of locally convex spaces in general, which Grothendieck worked with. So what do I mean by a star admissible topology? But before I even say that, here it becomes crucial that the multiplication on the algebraic tensor product be jointly continuous with respect to tau. Otherwise, the completion when taking the hat need not be an algebra. Okay, there's a lot in this definition, so I condensed it like this. So we take two locally convex star algebras, And then what we do is we take their involutive tensor product algebra. Then the topology tau will be star admissible if you have three conditions working out. First, when you take the tensor product, then tau is a locally convex star algebra having continuous multiplication, denoted like that. And by continuous multiplication, we mean jointly continuous multiplication. Secondly, the tensor map must be continuous, again, jointly continuous. And then lastly, if you take any two equicontinuous subsets M and N of the continuous duals A star B star of A and B, then if I just take all tensors, elementary tensors from M and N, then this again must be an equicontinuous subset of the dual, the continuous dual of the algebraic tensor product of A and B under tau. In other words, the tensor map preserves equicontinuous subsets. The tensor map is jointly continuous, and the multiplication on A tensor B is jointly continuous and is a locally convex star algebra. Those three conditions is actually a modification of compatible topology, and it also comes up in the general theory of tensor products of locally convex spaces. But now we have to adapt it to the algebra setup. So this then is what I mean by star admissible, all three of those conditions. Now I'd like to mention one result which goes back to Maria Fragolopoulou, Fabio Bagarello, Camillo Trapani, and Atsushi Norway. And it is actually a very nice way of actually constructing more examples of GB star algebras. Earlier on, I mentioned that if you take the topology on a GB star algebra, this one here, let's say you're restricted to the underlying C star algebra, then it's weaker than the norm topology. In this regard, now what we do is let us just start with a C star algebra, call it a norm. So that norm is a C star norm. And let us equip it with the topology tau in such a way that this A, so A again is the C star algebra, it is C star, but now A tau is a locally convex star algebra with jointly continuous multiplication, and such that tau is weaker than norm. Okay, so up until the full stop, A is a C star algebra, now equipped with two topologies. The one coming from the C star norm, making it a C star algebra, and the other coming from tau, which is locally convex star, jointly continuous multiplication, but tau is weaker than norm. Now, because the multiplication on A is jointly continuous with respect to tau, then this A tilde tau, the completion of A, is again an algebra, and it can be shown to be a star algebra. So we use this symbol to denote the tau completion of A, and then this is not just an algebra, but it's a GB star algebra over the tau closure of the closed unit ball of A. We remember that a GB star algebra has as its largest element in that class of sets the closed unit ball. In this case, the closed unit ball will be the tau closure of the closed. The largest element in B star will be the tau closure of the closed unit ball of A. So here's actually a nice way of giving us another example of a GB star algebra. This result is important as it motivates and is useful for one prototype example of a tensor product of two GB star algebras. This result that you see here is crucial for the next example, which is our prototype example. Okay, so we have a GB star algebra, and you let P lambda denote a family of star seminorms of A defining the topology. So that's just any random GB star algebra which is complete. Now we take a space X which is locally compact and Hausdorff, and then we look at CXA, the locally convex star algebra of all continuous A-valued functions on X. So now these functions are not complex valued, but they take their values in the GB star algebra A. So we remember A is our GB star algebra complete, and now CXA is all continuous functions on X which take its values in that GB star algebra A. Now what we can do is we can equip it with a topology defined by this family of seminorms, Q lambda F. How do we define it? It's the supremum over all elements X in K, where K is compact. And the lambda here comes from the indexing set lambda, which is part of the definition of the star of the seminorms defining the topology of A, the GB star algebra A. We notice f of x generally takes on its values in A, so f of x is in A, so talking about P lambda f of x makes sense. And now we take the supremum of P lambda f of x over all x in K, where this K over here is compact. In other words, we index our seminorms over all compact subsets of X and over all the seminorms appearing in the GB star algebra A. So it's a generalization of the compact open topology in CX when it's complex valued. In other words, when A over here are all the complex numbers. Then what one can also do is to show that under the biprojective tensorial topology, CXA is topologically star isomorphic to the tensor product of CX with A under epsilon, the completion thereof.
Yes.
And that's the biprojective one.
Injective of Grothendieck, yes?
Yes. Yes, that's correct. It's in that sense. So
Yes.
that's up to topological isomorphism. So what we have here then is an important example of one nice example of a GB star algebra. And to prove this result, you actually need the result on the previous slide, where you take a C star algebra, complete it with a weaker topology, making multiplication jointly continuous, and then that completion is GB star. That previous theorem of Fragolopoulou et al. Is crucial to making this thing work. Also, if A over here, if we start off with the GB star algebra being C star-like, especially that case, then one can again show that this thing is not only GB star, but then CXA is also C star-like. So here we get another example of a C star-like locally convex algebra. Another example is constructed. And in fact, you can now again construct an infinite number of examples of C star-like algebras, because you can just put in place of A here any random complete GB star algebra. And any random locally compact space X. All right, now this example actually served as the motivation for how on earth should we define tensor products in the general GB star case. This gave us the main result in our paper, and this the previous example that was crucial for this purpose. We start here with two GB star algebras, call them A1 tau 1, A2 tau 2, and we let this B01, B02 be the maximal members of B1 star and B2 star respectively. In other words, these are then basically the closed unit balls of the two underlying C-star algebras respectively. Now again, we define the star admissible topology on the algebraic tensor product. So again, that means making the topology, the multiplication jointly continuous, the tensor map jointly continuous, and then and any two tensors of equicontinuous sets again equicontinuous. So we mean it in that sense. Then one can show that the following are equivalent. This complete GB star algebra is GB star. That's GB star, this complete tensor product algebra. And one can say that if you now take that, one can find a norm, one can find a C-star norm on the algebraic tensor product of the two underlying C-star algebras. And then complete it and get a C-star algebra which is contained in the original GB star algebra. So this has to happen for some C-star norm. So it doesn't have to happen for any C-star norm, but it has to be for some C-star norm. So under these two, these two conditions can be shown to be equivalent. And in the previous example, to show the statement 1, we actually ended up showing statement 2. Okay, so what we notice here is that when you form the algebraic tensor product of A1, A2, and then equip it with that topology tau, and then complete it, it might not necessarily be a GB star algebra, but only when the equivalent condition 2 is satisfied. In a C-star algebra, condition 2 then is redundant, so that then the statement actually trivializes in the C-star algebra sense. Okay, so when the two conditions are met, then we will call it a tensor product GB star algebra of the two. I will now give you two examples of tensor products. The first, let's take any commutative C-star-like locally convex star algebra. So that, for example, could be the commutative Arens algebra. And now what we do is we let M and A be the star algebra of all n by n matrices over A. Then this M and A can be shown again to be the complete tensor product of AB and MNC with MNC. So AB is the underlying C-star algebra of A, of the C-star-like algebra. M and C are just the n by n matrices over C. Then this complete tensor product of the two spaces under the biprojective tensorial topology will give us M and A. Then this is C-star-like and hence a tensor product GB star algebra. And one can show this again using the previous theorem. So a matrix algebra over a C-star-like algebra is again C-star-like. And you do it by realizing this MNA as a tensor product. That's the interesting part behind it. Also, if you now take any C-star-like locally convex star algebra A, so in other words, that A that you see in that tensor product, any C-star-like algebra, then this L omega tensored with A, take the completion under the biprojective topology, then this is again tensor product, GB star algebra. And again, if you can put on any locally convex C-star-like algebra, and thereby you can construct an infinite number of examples of C-star-like locally convex star algebras, which are tensor products. So, for example, you could take A tau to be that also you can take it to be that non-commutative Arendt's algebra, which I have referred to sometime earlier on in my talk, and then get a tensor product. So again, one can see some non-commutative measure theory actually coming into play here. Okay, this is just a very quick summary of our work on tensor products, but you can read about it either in our paper or in our book, where we give further details and more results. Okay, I would like now to give the last part of the talk, which are applications to mathematical physics. Okay. Back in 2018, I was looking actually at how to incorporate unbounded operators and non-norm topological algebras, therefore, when looking at quantum entanglement. This was a paper which I had published back in 2018. So here I'm just going to give you the main concept. So quantum entanglement, and then this also included obtaining results on pure states of GB star algebras. But I think due to time constraints, I've decided to refrain from giving the results on the pure states, but just to give you an idea as to how I've defined quantum entanglement in the GB star case, and then to leave the details as to the applications and examples, therefore, in the paper, if you would ever like to see the paper. So just to give the main result, there's a lot happening here. Let's start here with we can start with two GB star algebras, if you like, A1 and A2. And then you complete it under some star admissible topology tau. So we are still working under the assumption of jointly continuous multiplication. And now what we do is we take a positive linear functional phi, and now we suppose that we can find a star representation going from the closable linear operators from D to D, and an element C in D, so that one can say phi of an elementary tensor is of this form. So we take X to be an A1, Y to be an A2, where for two given Hilbert spaces, H1 and H2, and their respective Hilbert space tensor product, D over here, this D that you see over here is just a dense subset of the complete Hilbert space tensor product. And then from that, then by linearity, one can then extend this displayed equation to the second displayed equation. Okay, but now when we are in this setup, we can say that a state, if we look at quantum mechanics, a state will be considered to be elementary if it is a tensor of two Hilbert space vectors of norm 1. But now we need to try and translate this across to the world of unbounded operator algebras, where things happen more abstractly. So then we take that definition 1 and we say, all right, a state phi will be separable if it can be expressed in the form 1 above, but now with the xi an elementary tensor, and then say that phi is entangled if phi can be expressed in the form 1 above, and you can never represent it in such a way that xi is an elementary tensor. This definition can be a little bit difficult to work with, because now it depends on how you represent the algebra. So another way to actually then think of entanglement is rather to just take the elementary tensor of two states on the algebra. Then it's actually more algebraic and less dependent on the way that you represent your algebras on a Hilbert space. But also in our paper, I've given some examples and a more detailed motivation behind it. But due to time constraints, I think I've decided not to give it here, but just to give the main idea as to the definition. Also, there in that paper, I also gave some results on pure states of GB star algebras, where I also gave some physical motivation behind it. As another application, I've looked at applications of GB star algebras to looking at quantum systems where the dynamics is actually irreversible. And this work is actually still ongoing. I did publish one paper last year as part of the ICTA proceedings, but it's still work that is very much ongoing. And it's happening on and off. Okay, so I would like to just give you an idea as to what's behind it. When we look at Schrödinger's theory of quantum mechanics, or equivalently the Heisenberg mechanics, there actually one sees how that translates to the dynamics of the system being represented by groups of star automorphisms on the algebra. Star automorphisms. So those are star homomorphisms of the algebra, which are bijective. But there are also, but this works really only when your system is reversible. The moment your system becomes irreversible, your quantum system becomes irreversible, then one cannot really work with star automorphism groups anymore. But then it has been discovered you have to work with star semi-groups of completely positive linear mappings. Any star automorphism can be shown to be a completely positive mapping. So when looking at quantum systems which are not, where the dynamics is not irreversible, you need to look at semi-groups of completely positive maps. So now that's what I want to start going into a little bit. Okay, so what do I mean by a completely positive map? I think we understand it in the C star case, but let's just make sure that we know what it is in the general scenario. We take a star algebra, and now we take the set. Now we can consider the set of all finite sums of the form x star x. And then this induces a partial ordering on the set of all self-adjoint elements of A. In other words, x minus y will be positive. X will be less than equal to y if x minus y is non-negative, in the sense that x minus y is such a finite sum. And now we will say a linear map will be called positive when phi of x is larger, is non-negative in the above sense whenever x is in PA. So in other words, takes positive elements to positive elements. So also larger or equal to 0 when phi x is a positive element in this sense. Remember that in a C-star algebra, it can be shown that an element is positive if it's exactly an element of the form x star x. But generally, we have to work with finite sums. And even in a GB star algebra, one can show an element to be positive when it's of the form x star x. But here we are looking at a general star algebra. The linear map phi will be called completely positive when the following happens. With a map phi going from A to B, you can take that phi and apply it to every entry in a matrix. So let's say we take a matrix whose entries come from A, and now we take, let's say, phi going from A to B, and we apply it to every matrix element. And then what we do is, let's say we take the entry in row I, column J, and then we form another matrix where in the same row I and the same column J, you replace it with phi of Aij. And then again, you form a matrix of elements in B. So Aij, every matrix element Aij in row I, column J gets replaced with phi of Aij in row I, column J, and this again forms a matrix. And we this mapping we denote by phi n, going from M in A to phi n to M in B. So we will say it is a completely positive linear map if this phi n defined as such is a positive linear map for every possible n. So this is how we define it in the C-star case, and this is also how we will talk about it here. Although in some references, completely positive map will be understood, will be defined in terms of bilinear forms. But for us, it's this case. M and A and M and B will denote the star algebra of all n by n matrices over A and B, respectively. So every completely positive map is a positive map. You just take n equal to 1, but not necessarily the converse. A positive linear map need not be completely positive. For those of you who are familiar with operator space theory and some quantum information theory, the completely positive map especially are useful as quantum channels. So in other words, they take because you want to take one density operator to another, representing a state. Okay, now what are these things all good for? Remember that now we have to work with semigroups of completely positive maps for representing the dynamics of irreversible systems. So one of my results, which I proved here, was that if you take a GB star algebra such that all M and A are GB star over M and A be 0, that need not be the case, but in the C star case it will be. Now you take a semigroup of unital completely positive linear mappings of A into itself, which has L as its generator. So we start with a semigroup of completely positive linear mappings of A into itself, generator L, then the domain of L, DL stands for the domain of L, will be a star subalgebra of A, well, we assume it. And the conclusion will be that you can show this type of inequality, which is almost like a dissipative linear map. And this also comes up in working with semigroup theory and Banach space theory. So one can necessarily show that. Proving the converse of this result, in other words, if we know that the generator satisfies this inequality, when will the semigroup be one consisting of completely positive maps? One such result, which I gave in my paper, is the following. Again, I'm only giving some of the results, but not all the results. So you start off in condition 1 by assuming that, because we want to give a converse. And then in addition to that, we assume that that you've got this, that the generator L, that the linear map L adheres to this form of continuity. So the constant you get depends on the lambda. For every lambda, you get the m lambda satisfying this for every x. Then L generates a one-parameter semigroup, first of all, of positive linear mappings, only positive linear mappings. But if we now go on to say that, or the Ln is what you get when you take L and you form the induced map on the matrix algebras. And if the Ln's then also satisfy the same type of inequality here, whenever x is in M and A, then one can show that these maps here are not only positive, but completely positive. So in summary, this condition here in the first proposition is actually a necessary condition in order to get completely positive. But you will have to assume quite a bit more in order to get it to be a sufficient condition. Now, something else over here, which I find rather interesting, and I will explain the relevance also to the mathematical physics point of view. And I am nearly finished. Okay. Right. Let's start here with the GB star algebra. M and A, again, GB star. We assume that M and A is GB star over M and A B0, but in such a way that AB0 is a hyperfinite factor which you can represent on a separable Hilbert space faithfully. In mathematical physics or quantum mechanics, we know the form of the Hamiltonian operator in Schrödinger's theory when the system is reversible. We would now like to know, if the system is irreversible, what would be the form of the generator? What does it generally look like? So this now is what the purpose of this proposition is about. We start with a semigroup of unital, completely positive linear mappings, which map A into itself. So that's like an irreversible quantum system for which the generator actually satisfies three conditions. It's a continuous linear map whose domain is A. First of all, the domain must be the whole entire A. When I restrict L to the underlying C-star algebra, AB0 is now the underlying C-star algebra of A. It maps AB0 into itself. And thirdly, it is ultra-weakly continuous. So just a reminder, we assume AB0 is not just a C-star algebra, but it's a hyperfinite factor on some separable Hilbert space. A is Frechet. And L is defined everywhere on A, and the restriction maps the hyperfinite factor to itself. Then you can get a self-adjoint element H, and you can get a positive linear mapping C, so that L is of this form. If we now go back to reversible dynamics, then we can take C over here to be the zero linear mapping, the zero map, so that the first term collapses to zero. Then you are just left with the commutator term, which is what we have in Schrödinger's picture. So for irreversible dynamics, now we can see the operator looks a little bit more complicated. One should be careful to use the word Hamiltonian because we don't necessarily have a self-adjoint operator here. And then furthermore, this term is actually something of the form here, C of x plus kx plus xk star for every x in A. So that's what I find rather interesting about this theorem. It tells us a little bit more about the generator. Lastly, to wrap up my talk, what about the converse? If this is now so crucial to have the operators, to have the generator of the form like that, when will it generate a completely positive linear mappings? So we start again with the same type of GB star algebra with MNA over being GB star over MNAB0. And you take a star linear map, which has this lovely form, which I have on top. But now where C over here is again a completely positive linear mapping, just like in the previous result. Then under such conditions, you can show that at least at L, when restricted to AB0, the underlying C star algebra of A is a semigroup with completely positive linear mappings of AB0 into itself. Okay, but hopefully many of these results are still, I can improve in the future. These are only just a few first results which I had published, and it's still work under construction. Okay, here ends my talk. I thank you very, very much for your attendance this afternoon, for your attention. And again, I thank you very much to Professor Hilemski and to Professor Pikowski for inviting me to give the talk.
No, mutually. Okay, so we thank very much our speaker. And what about questions? Who has? Hanar usually has.
Actually, I have two questions and one comment.
Yeah.
Okay.
Yes.
The first question is exactly about proposition 3.5. So what is k in the last line of your formula? A little k.
In the last line of my formula. Okay, k actually, well, it's what you would actually get when you simplify. So in other words, if you were to take that second last equation and you were, let's say, to tidy it up a little bit, then it actually can be rewritten in that particular form.
Oh, I see.
So it's actually just a simplification of that.
Yeah, I see. Thank you.
Yeah.
The second question is about a result, if I'm not mistaken, due to Fragolopoulou, Trapani, and Bagarello, which enables us to construct a JB star algebra out of a C star algebra. So I don't remember the exact page, but
You can go back.
The question is about relation of two C star algebras. So on the one hand, yeah, thank you. Exactly the theorem.
This one.
No, the theorem on the previous page.
There we go. There it is. Yes, exactly.
Yeah. So my question is, so here we start with the C star algebra, and we get a JB star algebra A tilde of tau. On the other hand, the very definition of JB star algebra involves a certain C star algebra, which is built over the max of the greatest member of B star. So my question is, how are they related? So if we start with a C star algebra A, then construct A tilde of tau, and then look at the respective C star algebra built over the greatest set in B star. So how these two algebras are related? Two sister
Okay.
algebras. Are they the same, or maybe they
They
are?
are, in fact,
can
they
they be
are
different?
actually the same.
The same,
When we take the tau closure of the closed unit ball of A,
Mhm.
then that will be the norm, that will be the closed unit ball of the underlying C star algebra of that. But now that underlying C star algebra is actually the same as the C star algebra you start with here.
I see. So the algebras, the two sister algebras are the same.
Yeah, they turn out to be the same.
Oh, thank you. And the last, not just a question, but maybe a comment about smooth, your notion of a smooth Fréchet algebra, where you so you define such algebras in terms of a certain family of seminorms. So can you show me the definition, please? Yeah. So my comment is that actually it follows from some old results due to Mityagin, Rulevich, and Jelasko that if there exists a family of seminorms satisfying this condition, then the algebra is actually locally M-convex. And so we can always find a defining family of submultiplicative seminorms. This is not 1960 something from 1960s.
Oh, okay. So okay. So are you saying it turns out to be locally M-convex?
Yeah. This was proved by Mityagin, Rulevich, and Jelasko in the 1960s.
Oh, okay. So if you okay. Now normally, yes. So you mean any such family makes it jointly continuous, therefore, locally M-convex.
Not only jointly continuous, but locally M-convex. Yes. So
Okay.
you can find, you can build an equivalent family of seminorms, which generate the same topology and which are submultiplicative.
Okay. All right. Okay. Thank you for that.
Yes. So, other questions? Okay.
So I had a question. So could you please open the fact that you had a normal element and derivation, as I guess a bit down. A bit down as well. So do you have a normal element, and you told about the functional calculus. I mean the holomorphic functional calculus. You took the value, and it, yes, this one. How does X relate to delta? Is it true that X from the D delta or not?
The X, okay, the X must actually be in the X must actually be in D delta to start with.
Yes. Oh, okay, yes. If X is delta, yes, then it's reasonable, but somehow it does relate. Otherwise, it's not true.
The X, we need to start with an X, an element of D delta.
I see. Okay, yes, I got it. Then it's fine. And one more question concerning, do you have sort of concept complete boundness or complete continuity for your stuff? I mean, GB star algebras. Not just positivity, but also sort of continuity or boundness by somehow.
I haven't thought about that yet.
I see.
I haven't actually thought about it. Completely bounded, then you would probably have to now one has to be careful. One has to think about what do we mean by boundedness.
I see. Yeah.
Do we mean continuity, or do we mean that we carry over boundedness structures?
I see, but probably you will need to define a special metric seminorms in a special way by somehow extend over all matrices, and the after you can talk. Okay, I got it. Yes, so that's not the case. Yeah. Okay. Yes. Thanks.
Okay. Other questions?
I have a question to Alexander Yakovlevich.
Yes.
Rinat. Because there were some problems with connection at the beginning of seminar, I have not here what you say about dates of my talk.
That's, so far either 10th of November or 17th of November.
More probably the 17th, because
17th, okay. Yeah. We shall try.
17th.
If not, we shall write emails, etc., and somehow we shall come to mutual. mutual
Because before you have said that at the end of November, and I have planned to 24.
No, it's 3rd of November is Yulia Kuznetsova, and then we have 10th and 17th, and maybe one of these will be to you or to Victor Semyon Schulman or to his Victorina Schulman. No, this we shall discuss with you later, Renat. And now, thank you very much, all people who were present, especially, of course, the speaker for this very interesting and also very well presented talk. This is very nice. And next time we shall have Oleg Yurievich Aristov. He will tell us about his recent results. Yes. So thanks for all, and we shall meet again next week. Okay.
Will I be receiving any the links to future seminars?
Yes.
Okay.
Yes, definitely.
Okay. Of course, we must provide it, and we are. It was stupid from my side, for example, that we were late to provide you with all topics, but now we know, and we shall try our best.
Sure.
Okay. So see you all next Friday. Bye.